Hello, welcome to our channel for the next chapter, some important problems, that is circles. And first we are going to learn the theorems. The tangent at any point of a circle is perpendicular to the radius through the point of contact. That is, here xy is a tangent and its point of contact with circle is P. And we have to prove that, you know that OP is radius, right? This OP is perpendicular to xy. That is what we are going to prove, right? And you see, for going into this, uh, see here you take this as O y1, y2, y3, right? That side O x1, x2, x3. Here you see uh, O y1 is the distance from the center to the circumference of the circle, that is to the on the circle, from the center to the point on the circle, it is radius, and there is some gap that I am going to take it as r plus a, right? Okay, now I am going to take it as r plus a, right? And this, the same way, here you see this OY2, this I am going to take, this is a radius and some distance here, I am going to take it as r plus b, and it is more than a, right? So I am going to take it as r plus b. In the same way, I am going to take it as r plus c. If you take this side, this is r plus d, right? That is, from the center to the circle, this is r and plus d, right? Then next, this is r plus e, and next r plus e, right? Next r plus f, right? Okay, now I am going to write it. Now listen, and you see OP is the radius r, right? Okay, now I am going to take here, what is that given? The given here is xy is the tangent, and P is the point of contact of the tangent with the circle. Now OP is the radius. OP is the radius, right? And what we have to prove? To prove is OP is perpendicular to xy. That is what we are going to prove, right? Now for this, I am going to take y1, y2, y3, and x1, x2, x3 on the tangent x comma xy, and join OY1, OY2, OY3, OX1, OX2, and OX3, right? And this is construction, right? And now we are going to take proof, right? We are going to do proof now. Now you see OY1 equal to R plus A, right? OY2 equal to R plus B. OY3 equal to R plus C, whereas OP equal to R. The same way, OX1 equal to R plus D. OX2 equal to R plus E. OX3 equal to R plus F. You see which is the shortest distance. Here you take, if you take OP is the shortest distance, right? OP is the shortest distance. And we from the picture we found out that OP is the shortest distance. Now we'll go to the next slide and we'll explain. And here, as OP is the shortest distance, it is perpendicular to xy. How is it perpendicular? And if you take two parallel lines, that is, here you see I have taken two parallel lines, AB and CD, right? These two lines are parallel. The shortest line between these 2 points is the perpendicular distance. We have studied already, perpendicular distance. Other distance will always be the longest one, because you see this will become a right angle triangle, hypotenuse is the longest side. So as this will become the hypotenuse, this will be the longest distance uh, between A and B. So the distance between the 2 points, if you take this O and this is P, the distance between this O and P is the shortest distance. As this is the shortest distance, it should be the perpendicular to that xy. Is it clear? So if you take any 2 points, the distance between the shortest distance between them is the perpendicular distance. Okay. So this is a what like theorem you should study, right? Okay. The shortest distance between the 2 points, that is AB, if you take, the shortest distance between the 2 points is the perpendicular distance. The shortest distance between the 2 points is its perpendicular distance. Hence, therefore, OP is perpendicular to xy, that is, radius is perpendicular to the tangent. Is it clear? We'll go to the next one. Next theorem is very, very important. The length of the tangent drawn from an external point to a circle are equal. See, here this P is a point where that tangent PQ and PR are drawn, and you have to prove that PQ equal to PR, right? Okay, and you have to write what is given. Given is PQ and PR are tangents. Okay, PQ and PR are tangents, and to prove is PQ equal to PR. PQ equal to PR, and we have to do proof, very, very easy proof it's, right? And you take the triangle OPQ and OPR. Triangle, you can see OPQ and OPR. Okay, you can say that OP equal to OP common. OP equal to OP common. See, here this is common, right? OP equal to OP common. Next is, if you take OQ equal to OR, that is radii, right? Okay, so now we see that this OQ equal to OR, this is radius, right? Okay. Now next is, last one is, we already studied that the angle between the tangent and the radius is 90. The angle between the tangent, PR is the tangent and OR is the radius, and the angle between the tangent and the radius is 90. The same way, PQ is a tangent, OQ is a radius, and the angle between PQ and OQ is 90. So that I am going to mark now, right? Okay. Now this angle, you see, this angle is 90 degree. This angle is what? 90 degree. That is what I am going to write. That is angle OQP equal to angle ORP equal to 90 degree. That is angle between the tangent and radius. Angle between the tangent and radius. Tangent and radius. Okay. Now you see by what congruence these two triangles are congruent. By right angle. This is see here, you see, this is right angle, hypotenuse and side. This is right angle, hypotenuse, side. So by RHS congruence, by RHS congruence, triangle OPQ is congruent to triangle OPR by CPCT. Corresponding parts of congruent triangle. CPCT means corresponding part of congruent triangle. PQ equal to PR. Hence, we proved the theorem. Thank you.